Welcome, everyone. My name is Nabila, and I am the Graph Neural Network stream owner here at ACE. For those of you that are new or here for the first time, ACE is a global community of machine learning practitioners and researchers who've gathered around topics in AI research, engineering, and products. We're currently working on creating a repo of authors talking about their own research because with all the new papers that are coming out every day, it's pretty hard to figure out what to pay attention to. So our hope is to make that process just a little bit easier by highlighting papers to our spotlight that might be of interest to the broader community. We host free live sessions like this 3 to 5 times a week, and we also produce premium content delivered in workshop format. Today, we're joined by Emanuele Rossi, who is a machine learning researcher at Twitter in London, where he works mainly on graph neural networks. Previously, he was working at Fabula AI, which was then later acquired by Twitter in June 2019. He completed a bachelor's in computer science at the Imperial College, and he has a master's from Cambridge University. His main research focus right now is on learning on dynamic graphs. Consequently, today the paper he's also presenting is Temporal Graph Networks for Deep Learning on Dynamic Graphs. So this is a paper that he teased at the ICML GRL workshop just last week, and it was super interesting to me. For those of you that are graph neural network enthusiasts, you'll know that technically we have graphs that are dynamic, but when we apply traditional GNN aggregation algorithms on them, we're treating them like they're static snapshots in time. And so these methods don't exactly take advantage of the dynamics of the data, which show that the graph kind of changes in time with the new node updates or edge updates. So what's cool about this paper is that Emanuele and his co-authors introduced memory modules that can learn the dynamics of this change in a graph, be it those node changes or edge changes. They also introduce a training strategy which helps them to train node embeddings with this learned memory, and they show significant performance boosts when compared to state-of-the-art approaches. So I'll let Emanuele talk us through this architecture. If you have any questions during this presentation, please post them in the YouTube live chat. You can also post those questions on Slack, LinkedIn live chat, or Facebook. And I'll relay them in the discussion round. So Emanuele is going to present for about 15 to 20 minutes uninterrupted. And any questions that we have, we will bombard him in the discussion round. So over to you, Emanuele. Thank you so much for joining us.
Thank you very much, Nabila, for having me. So yeah, today, as you said, we'll be presenting TGN, our new paper called Temporal Graph Networks for Dynamic Graphs. And this is work done in collaboration with all my colleagues at Twitter. So a little bit of background, I will go quite quickly over this. So as probably most of you know, graph neural networks are becoming very, very hot in machine learning. And here we have this image showing that basically, if you look at iClear submissions keywords, graph neural network is the basically fastest increasing keyword with respect to the previous year. So very, very hot. And the reason is quite clear, is because graphs are everywhere. So here we have a few examples. So a social network, molecules, functional networks which connect related part of the brain, and interaction networks, for instance, protein-to-protein interactions. And clearly, while one of the main success stories of deep learning has been computer vision, where we have convolutional neural networks, which are a very, very powerful tool, it's not clear how to use the same tools, such as convolution, to deal with graphs. So here on the left, we have an image, and we know that convolution works very well because we have a constant number of neighbors, and we have also fixer ordering of neighbors. So we know which pixel is on the top left of my central pixel, and so on. So we can apply a filter and move this filter over the image. Whereas when we move to graphs, this structure is not so clear anymore, since each node can have a different number of neighbors, so a different degree, and also there is no intrinsic order of neighbors. So there is no first neighbor or second neighbors, but they are all kind of equivalent in this sense. So basically, in the last few years, there has been a lot of work on trying to develop new models, which were very much inspired by convolutional neural networks, but specifically for graphs. And one of the most popular frameworks, we kind of generalize many of the models, is the message passing neural network, where basically the idea is to update the features of each node by aggregating basically representations from the neighbors. So as we see here, we want to get an updated representation for a node I, and we basically, each neighbor of I sends a message. So here we have a neighbor j, which sends to I a message mij, And on the left here, we see how these messages are computed. So each message is a function of the features of the two nodes involved in an edge, as well as possibly features on the edge itself. And then I will have to aggregate all the message coming from its own neighbors, and this will produce a new representation for I itself. And these can be, repeated in many layers, giving birth to, deep graph neural networks, which allow you to not only see the one-up neighbors, but further away in the graph. However, there is a problem that actually many graphs are dynamic, whereas even though much of the literature so far has only really considered the static graph case. So a static graph is a graph which basically is given and doesn't change in time. On the contrary, a dynamic graph is a graph which evolves over time. So for instance, you can have new nodes which appear over time, but also new edges, and also the features on the edges and the nodes can change. So here we have a classical example, which is inspired very much by the Twitter platform. So we have on the bottom here, we have users, and these users can follow each other. So we have follow relationship here in black, and each follow relationship comes at a specific timestamp. So I followed you a year ago, or you followed me 6 months ago. So the timestamp is quite important there. And also users can, for instance, interact with content. So for instance, they can post tweets. They can also like a tweet or follow a tweet, and they can also retweet another tweet. And all these edges have a timestamp, which is when the action was taken. And the tasks that we can envision here are multiple. And for instance, one may want to predict, is there going to be an edge between two users, a specific timestamp? So will this user follow this other user at this timestamp, or also will this user interact with this tweet? So this is a classic, they're both classic recommender system problems. So will this user interact with this tweet? So it's clearly, and this is one application, one example, but there are many. For instance, financial transaction networks, where you have, for instance, entities buying objects at specific times. And learning on dynamic graphs is very interesting, and is also not quite the same as learning on static graphs. So in particular, the setup that we have here is that our data is a sequence of ordered time events. So events can be anything like a new edge coming up, a new node coming up, but also features changing. In this presentation, for simplicity, we will mainly focus on new edges as the only event. And during training, an epoch is important that it goes through our events, so our edges or interactions, in chronological order. And in particular, even though this is not the only way a model for temporal graph can be trained, in this particular setting, in this particular scenario, we train the model self-supervised. So basically, we want to predict future edges, future interactions, using all the information that we have from previous edges, so edges that come before in time. So here, for instance, we go through the data, and we see one edge here on the right. And at start, without any information, we may want to try to predict whether this edge is going to appear. After that, we see a new edge, and using the previous edge, we want to predict this new edge, and then so on. We see one edge at a time, and we want to use all edges that we've seen before to predict the existence of this new edge, and so on. So let's go to the model. So in our paper, we introduced this new model, TGN, which is the shortcut for temporal graph networks. And in particular, our TGN is a model, is an encoder. And this is because basically all models for dynamic graphs can be seen through an encoder-decoder, to the encoder-decoder lens. So each model is an encoder-decoder pair. The encoder, in this case, is a model which is able to generate temporal node embeddings. So basically, should be able to generate embeddings for any node I at any time t. So here we denote that by z subscript I at time t. And given our TGN model, which outputs these temporal node embeddings, then we also have a decoder, which is task dependent. And for instance, if we want to predict edges, the decoder would take 2 node embeddings and predict the probability of that edge. And we have an example here in this diagram where we have a temporal graph, which is with edges from time t1 to t7, which are fed into our TGN. And the goal is to predict this dashed edge t8. To do so, our TGN computes embedding for node 2 and 4 at time t8 and feeds them into the decoder with just an MLP, which from their concatenation predicts a probability of this edge appearing. So TGN is a very general theoretical framework, and it consists of 5 different modules, which we'll go through in detail in a second. And also, it's very nice because it generalizes existing model for dynamic graphs, such as Jody and TGAT. Let's start going through the modules. So as we said, there are 5 modules. The first and probably most important is the memory. So the memory is really just a state or a vector for each node that the model has seen so far. And as such, it is a compressed representation of all the past interactions of a node. And it can be, you can think of it as basically the hidden state of an RNN. However, we have one memory, one vector for each node in the graph. Also, it's important to understand that the memory is not a parameter, even though the modules that we use to update the memory, are made of parameters. And for this reason, it can also be updated at test time. So after we finish training our model, and our model is now in production, is being deployed and is working, as we see new edges appearing, while we can try to predict these edges, when we see them appearing, we can also use them to update our memory. Since this is new information that we have, and we want our model state to always be up to date. This memory is initialized at 0, and it can very well also handle new nodes. So our model fits into the inductive scenario, where at test time, you have to make predictions about nodes that you haven't seen at training time. So here is a little diagram where we have a memory, and we have one vector for each node, 1, 2, and 3. But how is the memory updated? Well, the first component, which is important in updating the memory, is the message function. So given every time we have an interaction ij at some time t, the message function computes messages for both the source and the destination, so both I and j, and the messages will later be used to update the memory. So maybe let's first look at the diagram. So we have in our batch, we have 2 interactions, and for each interactions, our message function generates 2 messages. So the first 2 are for the first interaction, the second 2 are for the second interaction. So this, for instance, is a message for node 1, and the message is at time t1 because the interaction was at time t1. And here you have the equation, and the message, the important thing to understand is that the message only depends on the memory of the 2 nodes involved in interaction just before the interaction happens, so the previous memory that we have, when the interaction happens, so this time some t, and also the features of the interaction. So this is all the information we need to then update the memory, given an interaction. Then we also have the message aggregator, whose only purpose is basically to aggregate multiple messages for the same node in a batch. So as you see here, coming from the previous slide, in a batch, you can have node 2, which appears in multiple interactions in the same batch. So then we have 2 messages in this case for node 2. The message aggregator simply basically aggregates these 2 messages for the same node to then end up with having a single message for each node which appear in the batch. And we call these aggregated messages. After that, we have the module which actually updates the memory. So taking these aggregated messages and the previous state of the memory, which is here as subscript I at times t minus, so t minus is just the timestamp previous to time t, we then generate the updated version of the memory. And a very common implementation of this module is just using an RNN for which takes the memory, the previous memory, and the message, and it gives you the new memory. Then we have another module which is not used to update the memory, but is actually used to compute the final temporal embedding for each node. In particular, this module is used to solve the staleness problem. And the staleness problem comes from the fact that if we use the memory of a node directly as the embedding for the node, as other approaches do, so here, we always have a memory which is updated as we see new interactions. So we could say, okay, let's take the most recent memory for each node, and this could be our temporal embedding. However, what happens is that you incur in this staleness problem, where when a user has not been involved in an interaction for a long time, the memory goes out of date. So for instance, if a user on Twitter, stays logged off the platform for a year, its representation will be super out of date. Its memory will be super out of date. So how do we overcome this problem? So the next time the user comes to the platform, we can make meaningful recommendation, even if their interest has changed. To solve that, we use a graph aggregation. So the idea is that we can actually look and aggregate over the temporal graph of our node and look at the memories of also the neighbors in the temporal graph. And most likely, some of the neighbors of this user have actually been active even in the recent past. So we can actually aggregate information from them to get a more up-to-date representation for the central node. And the idea is that even if you have been logged out of the platform for a long time, the people you follow or that follow you probably some of them have been more active. So if the interest shift, we can also capture what has changed in your interest. And so here we see that from a batch, we generate node embeddings for each node in each interaction. And this, we do this aggregation over the temporal neighborhood, which is all the edges which happen before time t at which we want to compute them back, because of course we can't look in the future. So here is an overview of the overall architecture, or basically what happens when you process a batch. On one side, we have all the sequence of operations which perform a state update. So from edges, we compute messages, we aggregate them, and then we use them to update the memory for each node. And on the other side, we have what we can call prediction. So from the edges, we use the embedding module to compute embeddings for all nodes involved in these edges, and then we use these embeddings to try to predict these same edges here, and this would give us our loss. However, if you look at this diagram, basically you can see that our interactions serves both as our training target, because they're used to compute our loss, but also as the information which we use to update the memory. And so we need to decide, in which order do we do the operations. However, if we first update the memory, so basically would be we first go through this bottom path here, we first update the memory and then we do the prediction, what will happen is that basically we are predicting the same thing we just used to update our memory. So our memory would already contain the information about what we're trying to predict, and that would be like cheating. So the model would not be very helpful. If we do the opposite, and we predict before, so we go on the upper route here. So we first predict the edges, and then we update the memory. You can see that all these modules, the message function, the message aggregator, and the memory module, they don't influence the loss directly. So they don't receive a gradient, and so they can't be trained. The solution is actually, the intuition for the solution, and then you can look at the paper for more detail, but it's actually quite simple, and is to actually update the memory first, but not using the interaction from the same batch, which would cause a leak of information, but actually using interactions from previous batch, which we store. So here we have an actual accurate diagram with the order of operations. So initially, given a batch, we update the memory using what we call raw messages, which come from previous batches. So this is all the information we need to compute messages, but for interaction coming from previous batches. So not the same interactions that we have in the current batch. So these come from previous batches. We compute these messages, and same as before, we compute the memory. Then we compute the embeddings using the just updated memory, and we compute the loss. So as you can see here, the memory is using embeddings, and therefore all these modules here actually influence the loss. And at the end, we basically store the raw messages for these interactions in this batch in the raw message store. So next time we will need, in the next batch, we can actually do the same trick again of computing messages for all their interactions. Let's go to some of the experimental results. So we experimented on 3 data sets on the task of future edge prediction. So again, predicting future edges. So Wikipedia and Reddit are 2 bipartite data sets. So between user and Wikipedia pages and between users and Reddit posts, whereas Twitter is a user-to-user graph. I don't have time. We can discuss maybe a bit later more in detail, but you can clearly see here that both in the transductive case and in the inductive case, where you have new nodes that you have not seen during training at test time, our model, this is a specific implementation of our general framework, clearly outperforms all other previous models in both 3 data sets. What is more interesting probably is the ablation study, which gives us some very interesting insights. And what you can see here is that these light blue results come from all different specific implementations of our TGN framework. Then we have JODI, which is another method for dynamic graphs, and 2 versions of TGAT, which is also another method for dynamic graphs. So first of all, and this is on Wikipedia on future edge prediction task. So first of all, you can see that our method in general is faster, more accurate than other approaches. That having the memory, which is basically, we also tested 2 models which are identical, apart from one not having a memory. And it turns out that the model with the memory performs much, much better. Is this TGN attention here compared to TGN no-memory. So there is a huge gap, even though not having the memory makes the model much faster, since you don't have to update it. The embedding module is extremely important. So for instance, here TGN attention compared to this TGN identity, the only difference is that we have the graph embedding module, which solved the Staleness problem. And you can again see that the gap is very significant. And graph attention, we try different embedding modules, but when you use the graph is really the best you can do, and attention is again the best you can do. Then probably I won't talk about this because it's not that interesting, but actually what is interesting is that it turns out that having the memory makes it enough to have only one graph attention layer. So having 2 layers, it doesn't really help that much. It helps just a tiny bit, even if it's much lower. Whereas if you don't use the memory, you really need the 2 layers. So future work, we really are interested in having more very good benchmark data sets for dynamic graphs. And we think OGB, Open Graph Benchmark, is the right place where to have these data sets. So we're actually collaborating to bring some good benchmarks here. We're interested in trying a global graph-wise memory. We also want to investigate the scalability and also possibly propose methods to scale better. At the same time, it's also interesting to explore neural ODs to basically be able to continuously model the evolution of the memory, and also explore with new applications such as anomaly detection, possibly molecular pathways, financial transaction networks, and so on. So to conclude, we've seen how dynamic graphs are very common, but have received little attention so far. So we proposed TGN, which generalizes existing models and achieves state-of-the-art results on a variety of benchmarks. We also designed an efficient algorithm for training the memory-related module, and we have an ablation study, a detailed ablation study, which shows the importance of the modules and which specific implementation of the modules works best. Thank you very much, and I'm now open to questions. And yeah, follow me on Twitter if you want to see more work like this.
Follow me on Twitter. Follow me at work. Awesome. Thank you so much for that presentation. We've had some questions come in. I guess I want to start right up from the definition of dynamic graph. So I mentioned briefly in the introduction that there's like 2 graphs, dynamic and static, but there's actually another distinction, right? There's continuous and discrete time dynamic graphs. Could you comment on that and give us some insight on what that means?
Right. So I have a slide for that here. So basically, yeah, most of the work that has been done so far for so-called dynamic graphs has actually been on discrete time dynamic graphs, which is quite, in some way, a limiting scenario where your data is represented as a sequence of snapshots of graphs. So at some time t1, you know what the graph looks like at time t1, then you have no idea what happens, until time t2, and then at time t2 you're able to sample the graph again and see, that a lot has changed, and then you have no idea what happens until some other time t3, and then again they tell you, okay, you have all these new edges and these new nodes. So it's really a sequence of graphs, but you don't have this fine-grained timestamp on the edges, for instance. And this is what really, I think, makes continuous time dynamic graphs more interesting, is where for instance, each edge has a timestamp. And you can see it as a sequence of events, where events can be edges, but can also be new nodes, and can be feature changes for nodes or for edges. And each of these events has a timestamp, and we know exactly when anything has happened.
Okay, I see. So if I were to translate that discrete time to like a time series forecasting problem, it's at time step 1, it's at time step 5 in units of 5.
So you're asking what are the units of this thing?
And I was trying to draw a parallel to something that maybe the users do know, that we know, like in maybe time series forecasting, we have uniform steps of time. So those can be thought of as discrete time steps.
Yeah, exactly. Yeah, they could be. You could imagine that you're, as any other, signal, you could be sampling the graph at these times, and probably usually they are, equally spaced. You sample every, some of these graphs you have, you have it every month, so you have a snapshot for every month. So this T may be January, and then February, and then so on.
Right.
And you may want to predict what's going to happen the next month. Yeah.
Okay, but in the continuous time case, the timestamp is actually used as input?
As input to the model, you mean?
Yeah, as input to the model?
Yeah, I mean, somehow you can also use it here. In the discrete time dynamic graph scenario, you can also use it as input. For instance, if the timestamps are not equally spaced between them, it may be interesting to know a snapshot exactly when it was taken. But yeah, continuous time dynamic graphs is fundamental. So knowing when an edge happened is super important. For instance, in the experiments that we have, you can see that basically, and in general in interaction networks, the most recent edges very often are the most important. So if you drop that timing information on the edges, you lose a lot of predictive power.
Right. Okay. And you do touch on that later in the in your paper, so we'll come back to that. But there are some questions around the actual messaging part. I guess the first question is more of a clarification. So you said that in your framework, nodes have memories associated with them, and the memories get updated. But are there any memories associated with edges?
No, there are no memories associated with edges. Basically, probably because in all our tasks, the tasks are always node-wise tasks. So you want to, for instance, do node classification, or we have also experiments on node classification, dynamic node classification, or when you want to do future edge prediction. So it's an edge that you haven't seen that edge, so you can't have a memory for an edge you haven't seen, right? But you can see it as you have the memory for the two edges, for the two nodes, which would be the endpoint of the edge, and then you can, given these two memories, you can use that to predict whether there's going to be an edge. So we haven't actually thought about having a memory for an edge. Maybe it could be interesting if you want to do edge classification, maybe. However, I think you can always represent an edge as the memory of the two endpoints on the two nodes plus some edge features, I guess. But maybe there is an advantage of having an explicit edge memory.
Okay, I see. Yeah, because so in this work, your pseudo for the edge memory is like the two nodes next to it memory.
Exactly, yeah.
Okay, that makes sense, because if you're doing link prediction and stuff, it's technically between two nodes. Okay, I want to talk a little bit about the message function. So you said in this presentation, we're only going to focus on the edges, I believe you said. So in your message function, we're looking at two message functions, MSGS and MSGD, which are taking in previous memory of nodes I and J, a time step, and the edge features, is that EIJ of T?
Exactly.
Okay, and so those message S and message D functions, what are those?
So first of all, I mean, they are basically the same, only you need to have one for the source and one for the destination. Otherwise, you get into weird scenarios where you will get the same message whether you are the source or destination, which it's clearly not a good thing to have. And basically, they can be any learnable function. And in our experiments, they are. We actually only have we have what we call the identity. We see that it works very well to have the identity message function, which we call identity because it's basically just the concatenation of these inputs. However, you could have, if these edge features are very sophisticated, you may need to have an MLP here to better combine these inputs. So it will be an MLP on the concatenation of these inputs. But we tried that, and basically works very similarly with identity, where you concatenate them. But for the sake of generality, you can imagine that you may want a function which, given these inputs, compute a message. Can just be the concatenation of the inputs. Can be also if these inputs maybe are very big. So if your edge features are huge, you may want to have an MLP also to reduce the dimensionality, and so on.
Right, and that's commonly done, right? If you want to coarsen the representations through layers.
Yeah, exactly. Yeah.
Okay. Actually, we have a comment from Nelly in the audience asking if edge memory might be useful if you have a relational graph and want to capture different relations between nodes. Does that seem likely?
What do you mean exactly by a relational graph? Because I think all graphs are relational in the sense that you have relations between nodes, right?
Yeah.
You mean that your graphs, we have edges with different types of edges?
So I'm hoping Nelly will reply on that. But if there are different types of edges, then it comes back to that same thing. We could just use edge features, right? Because there could be different features for different types of edges.
Yeah, I mean, I think you can do. I would think you can do edge classification by having, the node memories and then the edge features. I wouldn't see why that wouldn't work, but maybe because I'm thinking, okay, you have a memory for the edges, and then you update it, for instance, when the changes that can happen to an edge is when either the edge features are updated or the node features are updated.
So you think it would be two updates for the same purpose?
Yeah, I'm thinking, I mean, you could have an edge memory, but I'm not sure about what benefit would bring rather than just having memory for nodes and then, as we were saying, concatenating them with also the edge features. I think would be very similar. But, maybe it would work better. You never know.
Yeah, everything is empirical, right? Most of it, at least. Okay, so there's a couple of audience questions relating to your experiments, and we'll get to those in a bit. But just to go back to your message aggregation functions, I just wanted to clarify. So each message here, all this message passing that's going on is not within graph structure, right? It's just updates, messages that are updates, not messages that are neighborhood messages.
Exactly. It's basically, well, the idea is that every time we see a new edge, so we said we go through the edges in time. We go through the edges chronologically, and basically every time we see a new edge, we have this new information. So we want to aggregate. So we want to incorporate this new information in our model, and in this case, in our memory. And the way we do that is basically we say, okay, each new edge generates messages for the source and the destination. And these messages is really just the information we need to then update the memory for these two nodes. So each edge generates two messages, and then we use these messages to update the node representation. So it's not part of the process of a graph convolution, but it is somehow it is coming from the graph in the sense that you have a message. It's quite similar in the sense that you don't generate all messages from all your neighbors at the same time, but you do them as you see them. So you do them sequentially. So each time you see a new neighbor, this guy will send you a message, right? This is basically what happening. So it can be seen through that lens, in the sense that every time a node adds a new edge, we know that there is this new edge, so we want to send a message from the neighbor to the node itself, and vice versa, right?
Okay, but it's not really spurred from neighbors, right? It's like more like at time step 1, what was the change? At time step 2, what was the change?
Yeah, exactly. It depends on it very much depends on when these edges appear. Yeah.
Okay, interesting. Yeah, because when I first read it, I was confused about how many types of aggregations there are, but actually those aggregations and stuff regarding the adjacency matrix, that comes up only in the embedding module of your work.
Yeah, exactly. So when you think about standard GNNs, we use a standard GNN only in the embedding module. However, the update to the memories, even though they don't have any GNN operations, they can be seen through the lens of a GNN operations, because basically you're sending messages, but not as you would usually do with message passing neural network, but only each time you have an event, you send a message.
Right, that makes sense. So on the note of, since we're talking about the embedding module now, there was a question from Reddit by Miguel Ventura. They wanted to know, this. There's multiple ways to encode a graph for a GNN model. We could either use the fixed size adjacency matrix, a sparse adjacency matrix, or sometimes even connectivity lists. So they wanted to know, which one did you guys use in your embedding, and why did you pick that?
Yeah, so what we do here is, so first of all, a detail that I haven't mentioned here, but we also perform sampling on the temporal graph because it may become very big. So for those of you which are familiar with GraphSage, we use the same neighbor sampling technique as GraphSage does. So let's say I want to compute the embedding for my node I only sample, let's say, a fixed number of neighbors. So let's say 10 neighbors, which would be neighbors in the real graph. So maybe I has a million neighbors, but I only sample 10. And then for all of these neighbors, if I have 2 layers, I need the 2 up to compute my convolution. So again, for the neighbors, I again sample 10 neighbors. So this basically prevents an explosion of neighbors. So basically, the idea is that for each node, we sample this 2 up neighborhood,
okay,
and then we recursively compute the aggregation. So it's not directly at least in the way they implemented, is not exactly as you usually would do with sparse operations, or we didn't use Python geometry, for instance, even though I think you could. And we would like very much to have dynamic graphs in Python geometric, and we're looking into that. But I think you could do it either way. But usually, for instance, you really want sparse operations.
I see. So it would be a sparse matrix that you construct for every node based on 2 hops away.
Yeah, exactly. Yeah.
Okay, that's interesting, because in your paper you mentioned scalability similar to GraphSage, and Ali from the audience on YouTube also asked that. Well, he said it sounds similar to GraphSage but more efficient. And I wanted to ask you to comment on that, but I guess you kind of have touched upon it.
So it's basically the only it's the graph. The only kind of bottleneck is the graph embedding module is what's heavy. And you also see in the ablation study, if you don't have the embedding module, basically, for instance, you're like 3 times faster. And then because the graph embedding module is what looks at the graph. And if you don't have this, we are more efficient. But basically, when you do this is kind of the same way as identically as GraphSage computes the embeddings. Apart from we use a different aggregation, so we use this graph attention, temporal attention, whereas GraphSage, they use mean or LSTM. They have different ways.
Right.
But the way we do, if you look at the GraphSages, these nice pictures where you build the computational graph and then you aggregate back. We do it the same. We sample the same way, and then we aggregate the same way. We just use a different aggregation. So from that point of view, that's why I say the scalability is the same.
I see. So on this note of embeddings, Parham from the audience on YouTube wants to know if you start the embeddings with previous embeddings, like for example, NLP-based embeddings, or do you simply learn them right from the start, like you randomly initialize and learn them right away?
Right. So yeah. So basically, the embeddings. So when we say we compute these embeddings, this is actually, we have like a functional form which is able to compute these embeddings. So our model, we don't have an explicit vector which contains this embedding, but it's actually our model. Sorry, our model. It's able to take any node I at any timestamp t and produce an embedding. However, it's a memory. It's a memory itself which is always there, and it is a vector, and we update. But this embedding, we don't keep them and update them. These are only used whenever you want to make a prediction at some time t for node I. You tell the model, okay, give me my embedding for node I at time t, and the way it generates this is just by going over the graph and looking at all the nodes' memory. So we can also continuous because it can generate the embedding for any time t. It's not only, we are not generate an embedding for every hour. Let's say anytime you want to, and it's important because you may want to make a recommendation at any time, right?
Mm-hmm.
So you need to have this functional form. Whereas the memory, it's what actually it's there and it changes in time, and it's initialized as 0. So basically you have to learn it as you go, and yeah.
Okay, so the only learnable part here is those message functions that compute my memory, and then when I want the embedding, I do inference to get some new time projection memory based on the time step, based on the memory.
Yeah, learnable are all these modules. So message function, aggregator, message aggregator, memory update to update the memory, and the embedding module, which is graph attention, which is also, of course, is also learnable, and the decoder, which is not part of TGN itself, but it's just a way to predict edges.
Okay. On that note, Chef Bordy one, sorry if I said that wrong, from YouTube wants to know if your experiments are based on labeled data.
So we have two types of experiments. So these ones that I showed are future edge prediction. So we call this self-supervised setting, in the sense that you don't need the labels, but you just predict future edges based on past events, past edges. So you go through your training data in order, and at each point you want to predict the next edge based on everything you've seen so far. And then your validation and test sets are disjoint in time. So validation is in the future with respect to training, and test is in the future with respect to validation. So this is basically, you don't need a label. However, we have this also experiments on dynamic node classification, which, for instance, in Wikipedia, you have labels on users, which tell you whether a specific time a user was banned. So we have labels for some users which were banned from Wikipedia at some time, and you want to predict whether a user was banned at that time. So for this one, you need the labels, yeah.
Okay, and these are temporal labels then?
Yeah, because a user is banned at a particular timestamp.
Okay, sorry, there's a bit of a lag, Emanuele. Do you mind saying the part about not leaving labels for the other tasks? So you said you are doing validation on future time steps and test on future from validation. But so how do you supervise the embeddings then?
So basically, your loss, your training target, is predicting future edges. So let's say, maybe let's go back here. Okay, so let's say I'm going through my epoch, right? And what I've seen so far is this data here. So at this point in time, I've used my memory and memory-related modules to update the memory based on these 4 interactions. And also I've used, so yeah, and I've got my memory. Now what I can do is I can use the graph embedding module to, let's say I want to predict this new edge at time t5 between 4 and 6. So given this data, I use my embedding module to compute an embedding for 4 and 6 at time t5. And then I feed these embeddings to the decoder. The decoder gives me a probability for this edge at time t5. And the probability, let's say it's 0.1. But I know that this edge happened, right? So I tell my model, okay, you're not doing very well. So I want this probability to be closer to 1. So this is how you supervise your model to have better embeddings. So the embeddings need to be predictive of future edges. And we also have negative samples. So we also train on edges which don't appear, and we want them to, probability to be close to 0 for them.
Okay, I see. That's why you call it, is it semi-supervised that you called it, or?
Self-supervised.
Okay, so you only need gradient updates for future predictions, not for current time steps.
So, I mean, what is a current timestamp? In the sense that you go through the edges in order, and then at any point you are at some time t and you want to predict what's going to happen next. So before t1, you don't have any information. You try to predict this edge between 1 and 2, and you're not going to do very well because you haven't seen anything so far. And then you see the first edge, and then you try to predict this edge between 2 and 3, and then you keep going. And by doing so, you learn your parameters to update the memory and also to produce the embedding, and so on. Is that clear, or?
Yeah, I think so. Yeah, it was more of a me question, but I think it's just that I misheard you and I wasn't sure. But thank you for that. Right. We've talked about the embeddings because it's a big part of your work, but could you talk again about the motivation for it? Because you said that in your paper, and I think you said in the presentation as well, that you've introduced it to combat staleness, which is a problem that you have if there's no interaction for a long period of time. But how do you evaluate staleness? Is it based on performance only?
Yeah, so that's a very good question. So we didn't experiment in very much detail about this particular problem. So it's a clear problem in the literature. It's been reported also in the recent survey from Borealis, and papers have tried to address it. And it's also very, very intuitive, right? And again, the idea is that if you only update the memory when a node is involved in an interaction. So, for instance, if I am on Twitter and you update my memory when I like a tweet or when I follow somebody, I can go away. I can say, okay, I'm not going to use Twitter for a year. However, and so you have no way to update my memory, right? Because I have not performed any actions. However, doesn't mean my interests haven't changed. In a year, I may become a fan of football again, even though I haven't been very much lately. So you have no way to when I come back to the platform, you have no way to encode this interest in my memory since I haven't done anything in a year. However, all the people that I follow, usually, especially if you follow your friends, if your interests change, also their interests will change, and so you may be able to find this shift in interest in the temporal neighbors of a given node, which may have been more active. Because if I have been away for a year, it doesn't mean my friends have been away for a year. They may have been very active. So by their actions, I can be able to infer something about myself, which is a typical claim of graph neural networks, that you want to learn something about me, and you do so by also looking at my friends or my neighbors. So I think it would be very interesting to actually maybe look at this problem more in detail, and the idea being, how does the performance worsen with respect to how long the memory is not being updated? So I can surely think of ways to test for this. So for instance, you can keep predicting future edges, but you stop updating the memory. So for, let's say, for a given node, when you see new interactions, you don't update the memory. So the memory, hopefully becomes stale, and then as you move further into the future, you are worse and worse at doing predictions if you don't use the graph.
Right.
Maybe using the graph, hopefully using the graph helps, and probably also hopefully using actually updating its memory with its own interactions, which you have discarded so far, also helps. So this may be an easy way to actually a more detailed experiment to test for staleness, which actually is very interesting. So thanks for doing
No
that.
worries. On that same note of staleness, though, is there a worry that as your graphs keep going dynamic, like adding more edges, adding more nodes, that your memory is going to saturate? Because you have only so much capacity, because we're not increasing the capacity of the model. We are just updating memory and using that memory to do inference. So at some point, your models will not be able to change their memory so much, right?
So the memory, as I was saying, is basically you can think of it as the hidden state of an RNN.
Okay.
So to update the memory, we actually use a GRU.
Okay.
So I think it should be. I think the problem with the RNNs is that is more about them forgetting what was very long in the past, very
Mhm.
very long in the past. But I think usually they are able to. I mean, that's LSTM and GRU. What they try to do is forget past information when they don't need it anymore to incorporate new information. So I think we shouldn't have too much trouble in that.
Yeah, okay, that makes sense. If you're using an LSTM, which is are somehow accounting for that by refreshing more recent changes.
Exactly, yeah.
Okay. So there's a question from Parham, which is also something I was wondering. What do you do when you have irregular node events in time? So this is a continuous graph or a continuous method, and so our time steps do not have to be uniformly distributed. So what do you do when it's not uniform in time? And Parham wants to know if you deal with those irregular time updates with ODEs, or is that what your ODE future work is intended to be?
Yeah, this is a great question. It's basically this. So it's something we've been thinking about very much since we published the paper. And clearly RNNs are not a principal way to handle irregular events, which we have here, because RNNs kind of assume regular regular samples. And so we are very much thinking about how to overcome this, and a clear, the most direct way to do that is actually using a continuous model such as neural these. Yeah. And
Okay,
there's been some work on graphs using neural these, but more for making the diffusion process continuous. So basically, instead of having layers of a GNN where you propagate through your neighbors, you kind of make these layers continuous. This paper also have some experiments with temporal data, but it's the discrete time setting. So they have snapshots which are irregularly sampled, so that's why it comes in handy to have neural these, but it's not a dynamic, continuous time dynamic graph. So I think there is definitely some room to incorporate this into models for continuous time dynamic graphs. And I think it's definitely the right way to go. And probably there's been also, I think outside the graph community, there is a lot of recent work, very interesting recent work on how to deal with irregularly sampled sequences. And I think most of it can be incorporated into graphs. And it would be very cool if we can also not only take that and use them in our scenario, but also maybe find a way to even make it more specific and better suited by using the specific structure that we have. So not just having this, as you would in a normal time series, and then add the graph on top, but maybe have a very nice combination of the two, which is a bit more specific. So if you're interested in this, I'm very keen to talk.
I'm going to invite you back in 4 months and hear about this paper that sounds that you're very interested in working on. Just in the interest of time, there's a couple more questions from the audience, and they relate to the experiments. So Marius wants to know, which is also, I think, a question I asked you, why is the improvement on the Twitter dataset so significant when compared to Reddit and Wikipedia?
Yeah, this is a good question. So to be completely honest, in the rush of the conference deadline, we did not have time to dig that much into detail on this. But it's something we should definitely do, and I hope I'll be able to do in the future. But for sure, what I can say is that sometimes you see the one model maybe is super tuned. The hyperparameters are tuned so much a lot for like a task, whereas the baselines are not tuned. I can say that is not the case here since we didn't really tune any of them. So even our model is not really tuned. We just use the same hyperparameter that we're using TGAT, and it worked all the time.
Okay.
So maybe we didn't put like that much effort into obtaining like the best possible performance with the other models, but we didn't even do that for our model. So we think it's kind of fair. We think the experimentation is quite fair.
That's interesting. We actually got a question about what hyperparameter tuning was done. So you're saying there was nothing?
Yeah, literally, because we just took the hyperparameters from TGAT, and they worked out of the box for our model. So basically, our model is quite similar to TGAT. So TGAT is a specific case. Even then, even what they did is not like they did a standard grid search. They tried like 3-4 values for the main parameters. Some of them they fix them by hand, so it's not one of these crazy tunings that you see nowadays. But we just took them and they worked out of the box very well. And the training, I have curves for these trainings, but they're all very, very stable trainings.
Flat and beautiful.
Yeah. So, but I will definitely look more in detail about the Twitter data set, exactly what's going on there.
Okay. Awesome. We have a couple more questions. I think they relate to the generality of TGN. So one of the questions from Sajid is like, why use GRUs for memory when there are models like NTMs that can use attention-based memory? I think you can answer this in 1 second. There's one more kind of related, which was, I lost it. How can TGNs handle edge attributes and potentially edge relationships? So these are kind of like, I think you're going to say that they're future work, or because TGN is so general, it can handle for all of these. But do you have any comments on that?
Yeah, so the first one, good question. No specific reason, but it's something something we quickly thought but did not investigate further. But it's possibly an interesting direction. So maybe also from the theoretical perspective, but also in experiments, having like a more general memory, which is as in memory networks, and then you update the memory through soft attention and you read from the memory and so on. So it's can be something worth thinking about. The second one is what is it again? Edge events.
It was regarding how do you handle edge attributes and potentially edge relationships, which we've probably touched upon, but maybe
so
they'd like to hear.
we do have them. For instance, here is E subscript ij. These are edge features, right? So, however, for instance, we don't have changing edge attributes. So the model is quite general, but unfortunately, the data that we have at the moment is not that rich. So we don't really have temporal updates to edge features or to node features. But it's certainly something we are interested in working on getting better data sets, which relates to the point I had here about better benchmarks. And in collaboration with OGB.
Okay, cool. We're almost out of time, but I'm hoping there's one more question that you can answer, which I think is possibly on everyone's mind. We want to start out with training these temporal or these dynamic graphs. How would we split the batch? Like, does a batch need to be a bunch of node updates or event updates that are on a per day basis or per minute or per hour? Like, how How do we split the graph to do these training process?
Yeah, actually, for our setup, you just need basically your data to be ordered by time, and then the batch can be basically any sequence of events. So they don't need to be all at the same time, or they don't need to be, a batch doesn't need to be, one day and then the next batch the same day, the next day. They just need to be ordered in time. That's all you need. And then the batch, you can split whenever you want, wherever you want.
Okay, because typically in GraphWorks, there's some complicated ways to split graphs for training, testing, validation, but you're saying just split it based on a random time threshold.
Yeah, you just need them to be in order. So you can't process your edges you can't shuffle your edges between going through an epoch, let's say.
Okay, that's awesome. We had so many questions, Emmanuel. This was a very engaging paper. I'm wondering if it's okay if some of these people reach out to you on Twitter or
Yeah,
online to follow up with you.
I'm very happy to do. Yeah.
Okay, awesome. So yeah, I think for any questions that we didn't get to, I apologize. We're out of time, but you can reach out to him on his work Twitter account, so he can answer you there. So I just want to say thank you again, Emmanuel, for joining us, sharing your work. Again, I'll follow up with you in the future if you finish that ODE paper. And thanks again, everyone, for tuning in. The slides will be posted at the event link on our website, ai.science. If you like this content, please make sure to subscribe to our channel, ML Papers Explained, to get notified about all our live sessions and all other free content that we do publish. So thanks again, guys. Until next time, see you.
Thank you.